Swayam Prabha. Digital India. Educated India.
So, in this class let us continue our discussion of lattice models. So, if you remember in the last class I had stopped here where I had explained how to derive something called the extended Hubbard model, starting from the description of a solid as being composed of localized positive charges, where negative charges, namely the electrons, are free to move. So, the lattice model by contrast is a model where electrons are not free to move spatially, but they are confined to specific points in the lattice. So, but then they are allowed to quantum tunnel through space, so that they can find themselves on the neighboring lattice point without passing through any intermediate spatial locations. So, that means in a lattice system an electron is either at some lattice point or it is found at a neighboring lattice point, etc. So, that means space itself has now been discretized into a collection of lattice points. So, the lattice description, basically the tight binding description of a solid, involves converting what was initially a homogeneous space into a space containing discrete collection of points. So, that means that an electron can either be at this point or at some other point, etc. It cannot be at any continuously in between, it cannot be in any other location. Okay, so, so that is the lattice description of a solid, that is the tight binding approach. So, in the tight binding approach, the kinetic energy of an electron manifests itself as a hopping. So, that means the electron can hop from one lattice site to a neighboring lattice site, which is described by this Tij, which refers to the hopping amplitude. So, it is the energy it gains by deciding to hop. So, that is why there is a minus sign, and I bracket j, ij within brackets basically means that you are looking at nearest neighbors. So, usually you confine yourself to nearest neighbors. But of course, like I told you earlier, that it is important to include higher order neighbors, that means the next nearest neighbors and so on, just to make sure that your results of that you are interested in do not change qualitatively when you make those modifications. So, that means there is some physical quantity that vanishes identically because you chose a model with the nearest neighbor hopping. There is some chance that quantity may not vanish identically if you include the next nearest neighbor hopping. So, if that physical quantity is interesting, it is very critical that you also include the next nearest neighbor hopping. So, similarly with Coulomb interactions of electrons. So, that means usually when you have Coulomb interaction, you obviously look, because it is a lattice model, an electron can actually sit on top of another electron on the same lattice point, provided one has upspin, the other has downspin, because of Pauli principle. Now, when they do, they certainly will have a strong Coulomb repulsion, which is described by this parameter called U. But then you can also have next nearest neighbor Coulomb interaction, and that is described by the next nearest neighbor interaction. So, this is called the extended Hubbard model. So, the inclusion of next nearest neighbor hopping next nearest neighbor, Coulomb interaction, all those things, they are called extended versions of the original simpler models. So, now it is possible, you see, once you allow for the possibility of introducing these parameters such as Tij and u and v and so on, nothing prevents you from becoming a little more adventurous and trying to write down models which do not necessarily have a derivation, systematic derivation the way I have derived this extended Hubbard model starting from R and P description. That means starting from the momentum and position descriptions of the electrons, I used a tight binding basis and all that, and then derived this. So, it is not in condensed matter, what one does is that one typically postulates certain Hamiltonian that we can intuitively feel are likely to capture certain phenomena that are of interest to us. So, one such seemingly ad hoc lattice model which is of immense interest in condensed matter physics, it is called the Anderson lattice model. So, that is the Anderson, this periodic Anderson model. So, the idea is that there are two types of fermions. One is what is called the itinerant fermions. Itinerant means mobile, electrons that move throughout the crystal. So, they are the ones who have prominent hopping amplitudes. So, that means they hop around from one side to another. So, itinerary, basically when you travel from one city to another, you make an itinerary. That means you tell yourself how you are going from say Guwahati to Bangalore. So, what are the stops in between? So, itinerary means a journey. So, itinerant electrons means electrons that perform a certain journey. So, the journey is that of hopping, they hop from one side to another, and so those are the itinerant electrons. So, they are denoted by Ci and C dagger I for annihilation and creation. So, now there is another unrelated species which are not itinerant, which are exactly the opposite of itinerant, which is localized. That means, these electrons denoted by symbol small letter d in this Hamiltonian, they are actually localized to the lattice sites. So, they are actually usually the d orbitals of the atoms. Means if you look at the if you remember your hydrogen atom orbitals, you have sp, df. So, the d has something like a meaning of a d orbital. You can think of it like that if you want, or you can think of it as some orbital which is somewhat localized. So, basically the idea is that there is some localized orbital, and the localized orbital will actually hybrid. So, that means that the idea is that the itinerant electron can undergo something called hybridization. Hybridization basically means it kind of trades places with this localized electron. So, that means the mobile electron can trade places with the localized electron. So, that means it can dislodge a localized electron and make it itinerant, or it can itself become localized. So, that means there is a possibility of that it's somewhat like there are some fictional stories where like Jekyll and Hyde, where there is the scientist who is a scientist by day and a monster by night. So, it is something like that. So, this electron can be itinerant, and then it can choose to change its character completely and become localized. So, that is achieved through something called hybridization. So, you might be wondering why people invoke such models. So, basically you will see that these models actually are very useful in describing what are called itinerant magnetism. That means magnets where electrical conduction also takes place. So, that means it exhibits magnetic properties, but it also exhibits electrical conduction. Say for typical example is iron. iron is strongly ferromagnetic, but it is also electrically conducting. So, that is an example of an itinerant magnet. So, generally speaking, people use these models in an ad hoc way to describe various realistic physical systems. Okay. So, but the key word here is ad hoc. That means that ad hoc means for that purpose in Latin. So, it may basically means it has just been invented for that particular purpose. So, there is no more fundamental derivation. So, this type of an point of view was advocated by this great physicist what many people consider as father of condensed matter physics, which is Philip Anderson of Princeton. He is no more, but he was very influential in this subject, and he is the one who gave a lot of prominence to these ad hoc lattice models, and many of them are named after him. And the thing is that they do capture a lot of interesting physics, but however none of them are easy to solve. So, it is easy to write. So, basically in condensed matter physics, if you adopt this ad hoc lattice approach, you can write down a large number of very interesting models that seemingly capture a plethora of very important interesting phenomena that you see in actual solids. However, sadly that is the extent to which you can go, because most of these models are exceedingly hard to solve, especially in more than one dimension where those materials actually exist. And because they are very hard to solve, you have to make a large number of approximations. Then it becomes less and less obvious whether those. So, if you encounter a discrepancy between theory and experiment, it becomes less and less obvious whether those discrepancies or the fact that theory and experiment do not agree very well, is that a result of the failure of the model or an inadequacy of the approximations. So, that becomes very hard to disentangle and very hard to judge. So, that is the reason why condensed matter physics continues to challenge physicists even now, and still there is no clear idea of how to. So, there is no actually a kind of a unified theory of condensed matter systems. Ideally, that would be nice. See, this ad hoc approach has the exact opposite effect intentionally, that it advocates the proliferation of unrelated models to describe a physical system. In fact, the same material is often described by different unrelated models, because the implication is there are phenomena which do not influence other phenomena even if they happen in the same material. So, it is prudent according to this philosophy to describe these different phenomena using different models, even though these phenomena occur in the same material. But that would be at odds with the ab initio or the first principles description of a material as being composed of just the fundamental constituents. So, that would really constitute a unified description of the substance from which all other phenomena that you see in that material should emerge. So, there are these completely divergent viewpoints that physicists often grapple with, and it is very hard to know which one will finally succeed, if any will at all. Okay, the point is that at this stage I have nothing more to add as far as lattice models are concerned, because as I told you that once you accept this philosophy of writing down ad hoc models, then you can write a bunch of them with relative ease, and they seemingly capture interesting phenomena, but they are impossible to solve very easily. fact, you have to make a whole bunch of approximations. But however, it is important to understand that suppose by some accident you are able to solve some of these models, maybe you will reach a stage where there might be a quantum computer in the future that can simulate these lattice models exactly, and that would pretty much take care of everything. So, in that eventuality, it is important for us to know what are the interesting questions to ask and answer with regard to these models. So, the idea is that, so I am just going to read off this paragraph, which is reasonably well written. So, it says, having derived the lattice version of the Hamiltonian of mutually interacting particles, we are now faced with the prospect of deducing its properties. Okay, so, by this one means computing what is known as the phase diagram. The phase diagram of the system consists of the following ingredients. Firstly, there are three mutually perpendicular axes, one each for temperature, number of particles per site, that means total number of fermions, the total number of electrons divided by total number of sites, and then there is lastly the ratio which describes the strength, the relative strength of the Coulomb repulsion versus the hopping. So, basically it tells you whether kinetic energy is more important or potential energy is more important. So, U by T is basically the ratio of the potential versus kinetic energy. So, that means you see that the phase diagram consists firstly of three axes. So, these are the three axes, and within this, so that means in this octant or whatever, so there are regions which are identified, and these are regions are called phases, and these regions are separated by surfaces, and the surfaces represent a boundary across which a phase transition takes place. A phase is characterized by a set of non-vanishing order parameters. So, an order parameter is an operator that has a non-vanishing expectation value in that phase. Okay. So, it is more convenient to use the following definition. So, imagine the script O bracket I, that means basically it is some operator which is made of creation and annihilation operator of the electrons. So, imagine something like C dagger I, Ci plus 1, something like that. So, Ci up into Ci down, Ci dagger up into Ci down, something like that. So, that sort of thing. So, these are typical, I mean you can have many such operators, but bottom line is something like that. So, that operator and I is basically a lattice point. So, now the idea is that if some operator deserves to be called an order parameter, it had better obey this property, namely it has to obey this property. That is, if you take the average of O dagger I into Oj and you make I and j far apart. So, remember that I and j are the lattice points. So, I am talking about a lattice model. So, if I and j are far apart, the idea is that they become OI and OJ are uncorrelated. So, that means the average of the product is same as the product of the averages. So, in that case, we say that the system possesses long range order with respect to this order parameter. Okay. And typically what happens is that, so in other words, if the system is in some well defined phase, you will always be able to identify such an order parameter. Okay. So, whereas when it is not in that phase, the average between OI and OI dagger, OI dagger and OJ will actually not separate out that way, but however the correlation actually vanishes. So, that means this product basically vanishes as the separation between I and j increase. So, what that means is that this particular operator certainly does not describe any particular order. So, the system is not ordered in any ordered phase according to that particular operator. So, you can cook up many such operators OI from by combining C dagger I up and Ci plus 1 down or whatever it is, you can cook up many such operators. So, the question is you have to find one such operator or several such operators which obeys equation 9.50. So, only then you can say that the system is has an order described by that order parameter. So, when you are successful only you can, when you are successful in verifying 9.50 only you can say the system has a well defined order, and you can write down, you can label that phase as that by that particular order parameter. But when you are unsuccessful in finding such an order, so that means any random O that you construct will typically obey not 9.50, it will typically obey 9.51. So, what it basically will say is that there is no relation between OI and OJ unless they are pretty much, I and J are pretty much the same things. So, that means so they are completely uncorrelated. But in one dimension what will happen is that, so this 9.50 is typical in for systems in 3 dimensions. But what will happen, there is a theorem called Mermin-Wagner theorem which says that you can never have something like 9.50 in one dimension. So, in one dimension the next best thing you can have is this. So, that means that instead of being a constant, so you see these are constants because in a translationally invariant system OI average will be independent of I. So, instead of being a constant it will actually become some power law. So, this is the best you can manage. So, remember that you might think that how are these two more or less the same. Well, they are 9.50 and 9.52 are closer to each other compared to 9.50 and 9.51. See, 9.51 tells you that the correlation between I and J exponentially decays as you move away, as I moves away from J, whereas 9.50 says that pretty much they are always correlated, that means regardless of. So, that means if I and J are far apart, they will or they are close by, they are more or less close by or far apart makes no difference, they are equally correlated. So, these are diametrically opposite properties. So, if an operator obeys 9.50, that means you have stumbled upon an order in the system. But when you are unsuccessful in finding such an operator, invariably you will be repeatedly verifying that 9.51 is the valid statement. That means any random O that you construct typically will obey 9.51. Very rarely you will stumble upon an O that will obey 9.50, in which case you are in luck. So, you can go ahead and label that particular phase by that operator. But however, in one dimension you will never be able to stumble upon any operator which obeys 9.50. The best you will do is end up with something called 9.52. Of course, you will always be able to, I mean any random thing you come across will always obey 9.51 in any dimension, but occasionally in one dimension you might stumble upon something that obeys 9.52, in which case you have to be content at that, because you will never be able to verify anything resembling 9.50 in one dimension because of Mermin-Wagner theorem. Okay. So, I kept on very mysteriously talking about order parameters or operators without telling you how to construct them. So, here are some concrete examples of orders. So, there is something called the charge density wave order. So, where basically what you do is the psi is the fermion annihilation. So, you create the total number of up and down spins at some lattice point I. So, that is basically the total density of fermions. So, that is called the charge density wave because it sums over all the spins. So, that means if you see now if OI and OJ, if you take averages, what will happen is that if I and J, if you make them far apart, they are still correlated. What that means is that there is a kind of an that means the electrons have decided to order themselves spatially. See, remember that this represents the total density of electrons at site I. So, if I and j, if the density of electrons at I is correlated with density of electrons at j, even when I and j are very far apart, what does that mean? So, that would be the case if 9.50 is verified using this construction. So, if that is the case, what that means physically is that the electrons have decided to spatially order themselves. That means that there is there is some spatial periodicity, for example, in the density of the electron. So, that is why it is called a charge density wave, right. So, it is charge as opposed to spin. So, that means you have summed over all the spins. So, it describes a charge. So, now you could also describe a spin density wave, where you stick in your Pauli matrix, which now describes spins in various directions, spin components in various directions, and that would describe your spin density wave. So, if you are able to verify 9.50 using this order parameter, then it means that there is some sort of a magnetic order in your system. So, that the electrons have kind of their spins have arranged themselves in some orderly fashion. But however, you do not have to necessarily first destroy and then create. That means, your order parameter does not have to conserve the number of electrons. So, in superconductivity, there are order parameters that do not conserve the number of electrons. So, as you very well know, superconductivity is described by Cooper pairs. See, in these first two examples, you are actually creating an electron hole pair. That means, you are first annihilating an electron, then creating an electron. So, that is basically like saying creating a hole and creating an electron. So, basically you are creating an electron hole pair in the first two examples. So, whereas here you are actually creating two holes or annihilating two holes, or creating two electrons and annihilating two electrons. So, that would be typical in a superconductor, because the order parameter there, it does not refers to creation of electron and a hole pair, but two electrons themselves form an order pair. So, that is called a Cooper pair. So, Cooper pair is where you have one electron with upspin typically and one electron with downspin. Okay. So, that is called the singlet superconductor, because that forces one electron to be up. So, sigma, and this is minus sigma, because sigma dash equals sigma. So, you create one electron with upspin and down, or annihilate one electron with upspin, annihilate one electron with downspin. So, you are creating a hole with upspin, hole with downspin simultaneously at lattice point I. And if that obeys, if that operator obeys 9.50, so what that means is that there is a phase characterized by this order, this peculiar order. So, this peculiar order is complex. See, unlike these are real order, the expectation values of these quantities are real, whereas the expectation of these superconducting order parameters are typically complex. Okay, so, the complex numbers have their own peculiar properties. They will have a magnitude and a phase. So, that phase has some important intrinsic physical meanings, so which we will not go into, but traditionally those were discovered first, historically speaking, and this is a modern more condensed matter version, field theory version of or description of superconductors. But this came later. Historically speaking, the description of that in terms of phases and so on, they came earlier. So, then you have this singlet superconductor, where you have up and down spin. That means, you create and annihilate two electrons, one with up, one with down. But you can also have a situation where you can have other types of superconductors, where you can, so this is called the S wave superconductors. You can have P wave superconductors, where you create two electrons, one with up and one with again with up, but then you have to make sure that there are other indices that distinguish, otherwise because of Pauli principle that order parameter will be identically 0. So, you will have to have different say orbital angular momentum states. So, that means you should be creating one electron with a certain orbital angular moment, the other one with a different orbital angular momentum. So, that is called P wave superconductor. You can have S wave, P wave, singlet, triplet superconductivity and so on. So, these are all the different possibilities. Okay. So, I am not going to, of course, finally verifying 9.50 involves being able to calculate this average, which is of course not at all an easy task, because this is a many body problem. Calculating this sort of average of O dagger I O j for a Hamiltonian such as 9.49 or 9.48 is exceedingly difficult, and it's nothing much is known. Okay. But I have at least told you what is worth doing in case somebody comes up with a very effective tool in the future, say such as quantum computers typically. Analytically, it is quite hopeless. Okay, so in the next class, I will be describing some approximation schemes which are controlled, in the sense that you can justify them somewhat mathematically as a systematic expansion in powers of something. So, we will be able to show that such a systematic expansion, one such expansion is called the Schrieffer-Wolff transformation. So, which enables us to show that there is a limit in which this sort of Hubbard type of model can be mapped into something called a TJ model, which describes antiferromagnetism. Okay. So, that means models that describe ferromagnetism, antiferromagnetism and so on, that is magnetic insulators, can be obtained by studying a suitable limit of the Hubbard model. That is interesting to know, because you see the Hubbard model describes itinerant electrons and Coulomb repulsion. So, it is nice to know that there is some limit in which electrons which are repelling through Coulomb interaction and they are just moving around kinetically, there is a limit in which they behave like a magnetic material. That means that how does magnetism, ferromagnetism specifically come about, or antiferromagnetism, how does it come about? After all, everything is finally made of electrons that are running around here and there and repelling each other. So, it is nice to know that there is some limit in which magnetism comes out, a magnetic material comes out of such a generic description of a solid quite naturally. So, that is worth doing, and I am going to do that the first thing next class. Okay. So, I am going to stop here. I hope to see you in the next class for Schrieffer-Wolff transformation. Thank you.